Hello everyone, and thank you for joining this workshop. So let's just get started. As I said in the chat window, please, any questions you may have during the workshop, just ask in there. I'll be reading the chat window always. So there we go. What are we going to do in this workshop? We have some IQ recordings. These are digital recordings of radio signals transmitted from real deep space probes. And we're going to use GNU Radio to analyze these signals, find these specifications. This is a simple reverse engineering. I call it simple because the specifications are well detailed. It's just we don't know a few of the parameters or what kind of codes are used. This will be clear throughout the workshop. And then as we go analyze these signals, we will build a decoder to decode the telemetry from this spacecraft. Why could anyone be interested in doing this? Well, first of all, I think it's very cool to go and actually receive real telemetry from spacecraft which are going into the depths of the solar system. Second, it's actually not so difficult. Many times beginners to GNU Radio tell me, well, I have this key fob, which is a garage door opener or a car key or something like that. It transmits ASK, amplitude shift keying. I want to decode it. And this is not so easy, actually, because it's a bursty transmission. It consists of short bursts. Slicing ASK modulation is not so trivial. So here we have this deep spacecraft telemetry, which is a constant signal, and it's actually easier to decode than your typical remote control. And maybe you're also interested in learning how deep space communications work. So what's better than having first-hand experience? The focus of this workshop is hands-on with GNU Radio, actually with GNU Radio Companion. I'm going to try and build the decoder in real time during the workshop. You already have with the workshop material the steps in which I'm going to build the decoder. So if you're following along and maybe fall behind, don't worry, you can just load the proper step and skip ahead. And maybe if I'm running short on time, I will also cheat, and instead of doing everything by hand, just load up some of the pre-dawn flow graphs. But the organizers of the conference made a very good suggestion to keep a balance between theory and practice. So I've also included some theoretical background in the slides. This means there is some math in the slides. If you understand the math, then that's great. If you don't, then that's also great. It seems some attendee doesn't have any audio. Is it the same for everyone? Okay, so just a local problem, thank you. So if you don't understand the math, I'm going to try to explain in simple terms what it means. And then if you want to study the math, you can always come back to the slides and look it up later. The spacecraft we're going to use are ESA Solar Orbiter, which was launched in February this year towards the Sun. It will study the Sun's atmosphere and solar wind. And also Bepi Colombo, which is a joint ESA and JAXA mission to Mercury. It launched 2 years ago, but on its way to Mercury, it did actually on April this year an Earth flyby. It will do several flybys around Venus. So the recording is of the Earth flyby on April this year. And as you can see in the diagram here, this spacecraft actually consists of different modules which are going to break up upon arrival to Mercury and orbit and perform different experiments. So you already have in the workshop material, if you downloaded the IQ recordings, a recording for Solar Orbiter, which is the main one I'm going to use, and also a recording for Bepi Colombo. What does it take one to receive these kind of signals? Well, these signals are transmitted in X-band around 8.4 gigahertz. The signal can actually be detected with small dishes you may have on your garden. I'm talking about maybe a couple meters dish size from long distances, from Jupiter, Saturn. But if we want to demodulate the data, then the spacecraft needs to be quite close to Earth. Keep in mind that these spacecraft are usually received with dishes of 34 or 70 meters. And the recordings we have here are either taken shortly after launch in the case of Solar Orbiter, or around the Earth flyby in the case of Bepi Colombo. But actually more than this is possible. Paul, who is the person in the UK who made the recordings I'm using here, is currently, so as of today, demodulating Tianwen-1. This is a Mars probe to Mars at a distance of 16 million kilometers. I really cannot imagine 16 million kilometers. So to help put these numbers into perspective, the Earth to the Moon distance is around 0.8 million kilometers, and light takes 10 seconds to travel 3 million kilometers. So this means that Tianwen-1 is so far that the signal takes almost a minute to arrive to Paul's station. This is Paul's antenna on his garden. It's a 2.4 meter antenna, and on the top, the structure you see here is typical microwave receive equipment. You have a microwave feed, an LNA, a down converter to get the signal into a suitable intermediate frequency running throughout the coax and into Paul's home, where he has an SDR receiver. I'm not so sure about the model he uses. So let's get on to analyzing this recording. The first step, whenever we have any signal and want to look at it, is to look either at the spectrum or the waterfall. The mathematics behind is to use the Fourier transform to pass from time domain to frequency domain. In GNU Radio, we can use the GUI frequency sync to view the spectrum and the waterfall sync to view the waterfall. And it's also a very good tool by Mike Walters in Spectrum. You can use it to view the waterfall of the recording. And if you're using the Ubuntu VM provided with the conference, in Spectrum is also installed. So let's move on to the hands-on section number 1. Hopefully my screen will come on. Yes, and here I have GNU Radio Companion working. This is where I'll be working most of the time. I also have loaded up the virtual machine in case anyone is using it and has specific questions about the virtual machine. So my recommendation is either you have downloaded the base virtual machine and then downloaded GRCon Workshop, or you already downloaded the virtual machine which has GRCon Workshop and all the dependencies included. But my suggestion is go into the GRCon 2020 workshop and run GNU Radio Companion from here, because all the flow graphs use relative paths to load up the recordings. So it's better to run GNU Radio Companion from here. In any case, here we are at GNU Radio Companion at an empty flow graph, and the first thing we need to do is just give it a name, workshop maybe, and then we want to load up our recording. So we use the WAV file source. What I'm doing here is going to the list of blocks and pressing Ctrl F to search for the block, then WAV file source. I'm going to pick here the recording of Solar Orbiter. And then this is an IQ recording. I need 2 channels. Of course, you need to know the format of the IQ recording you're using. So another thing I need to use is the sample rate. The sample rate, I don't know it by heart, so I'm going to cheat and look it up. It's 2016129, so nearly 2 megahertz. If you did this recording yourselves, then you of course know the sample rate. And if not, then you can examine the WAV file headers. So then we have two real channels, the I channel and the Q channel. In GNU Radio, we usually work with complex signals, and the way to convert from two real channels to one complex signal is to use flow to complex. So orange means a real signal in GNU Radio, and blue means a complex signal. In here, we are just putting the I and the Q together as a complex number. And then we can use the GUI frequency sync. One thing I like to change is the default size of the FFT size. I like to use 4096 points. This will give me better resolution on the spectrum. And now I can run. And this will ask me to save my flow graph somewhere. So there we see it's running. And this is the spectrum of the signal. If we zoom in a little bit, we can see a spike in the middle. This is the carrier. We'll surely see what it means. And some sidebands, which are the data modulation. It's easier to see this if we do some averaging. So averaging can be configured here. We can use median averaging, for instance. And then the spectrum is not so noisy anymore, and we can easily recognize the shape of the data modulation, and this is the residual carrier. So let's close this and go back to the slides. So you raised your hand. I'm sorry, I don't know where to see that. Just type your question in. And I'm not sure if the questions you type, so this chat is going to appear in the recording. We tested this yesterday, and the slides are in the recording, and also the shared screen, but I'm not sure about the chat. So, okay, let's move on. This is actually some of the math involved. So the thing you need to know here is that deep space communications use residual carrier phase modulation. This means that we move the phase of a signal, and usually we work with IQ signals. This means complex baseband representation. So our signal is an exponential where we move the phase around. What does this phase look like? Well, it has some deviation, which kind of sets the amplitude of the modulation. Then we have a subcarrier, which might be a sine wave or a square wave, and we'll see why this is done. And then we have the data modulation, which is just a non-return to zero signal, an NRZ signal. This is just ones and minus ones for the bits. And Manchester encoding is a special case of this. And the way it works is, well, for a subcarrier frequency, which is equal to the symbol rate, we have Manchester encoding. We'll see some pictures about it. The residual carrier, which is the spike you saw in the center of the spectrum, is used to help the receiver recover the carrier phase of the signal. This is essential for demodulation in very weak signal conditions that these spacecraft signals typically face, as they are very, very away, very, very far from Earth. It is also possible to use suppressed carrier modulations which don't have a residual carrier spike, and this is often used for very high-speed data. Here we have some pictures of the spectrum of how this signal may look like depending on the choice of this subcarrier. And the main reason why we use a subcarrier is to push the data sidebands away from the central residual suppressed carrier. So here we have just a normal subcarrier. The data sidebands are to the sides, well away from the residual carrier. So here the receiver can go and look at the residual carrier, and the data sidebands don't interfere with it because they are separated in frequency. If we drive the data sidebands towards the middle, then we arrive to Manchester modulation, where we have this gap in the middle for the residual carrier, but the data subcarriers are very close to it. And on the very extreme, where we don't have any subcarrier, then we have baseband modulation. The data is just on top of the subcarrier and it is interfering with it. So this is only used for high-speed signals where you don't want to use as much bandwidth as you need to separate using the subcarrier. So in our case, we see that the spectrum we saw looks very much like this Manchester picture. So this is what we're dealing with. Let's get to carrier phase recovery. So the transmitter is transmitting the residual carrier, which is mathematically represented by a number 1, and then the data, which is what we are mainly interested in. But in the receiver, we receive not this original signal, but a signal which has a different frequency and phase to what was being transmitted. This is mainly because of 2 reasons. First reason, the transmitter and receiver local oscillators are not synchronized in phase. And second, because in changes of the propagation path, so in particular, the spacecraft is moving, there is Doppler shift. So we have this moving frequency. What we use is a PLL, which is a device that can detect and track the frequency of the and the phase of the residual carrier, and then correct for it and cancel this extra term which we don't want. This is used. This is done with the PLL carrier tracking GNU Radio block. Many of the blocks which do a control loop inside GNU Radio assume an amplitude of 1. So if we don't have an amplitude of 1 in our signal, such as in this case, we need an AGC, an automatic gain control block, before the PLL. And in this case, I'm going to use the RMS AGC block from GR Satellite, just because I like it, but there are also suitable blocks included in GNU Radio. They're also called AGC. So let's move on to hands-on number 2. And then, waiting for my screen to come up. There it is. Here, as said, I'm going to use RMS AGC. I put it just in the middle of the signal. And this is going to automatically adjust the amplitude of my signal, whatever it is. The reference 1 is the amplitude I want to achieve, so that's okay. And the alpha controls how fast the block responds for this signal, which doesn't have large changes in amplitude. A low alpha, such as 10 to the minus 5, is fine. And then here we insert a PLL carrier tracking. I'm going to do something. We are going to compare the input of the PLL with the output of the PLL. So I set here 2 inputs so we can compare. And now we have some parameters we need to decide. For this, I'm going to use variables. So the variable block can be used to define a variable. We can just give it any name. And we need the PLL bandwidth. The PLL bandwidth I typically write it in hertz. And again, it's a measure of how fast the PLL responds. If you put a very low bandwidth, then the output of the PLL is not very noisy, so this is good. But it might lose log if the signal moves around a lot. On the contrary, if we put a large PLL bandwidth, then it's easier to track the signal variations, but you'll get a much more noisy output. In this case, 100 Hertz is okay. And then we also have a variable which I can use to set the PLL limit. This is the frequency limit. it will try to lock on, so 10 kilohertz is okay. And something important about many of these blocks is the units. In the documentation, you probably can see the units are not hertz, but rather radians per sample. So to convert from hertz to radians per sample, we can multiply by 2 pi and divide over the sample rate. And here I'm using pi. Where can I get pi from? There is something very useful in GNU Radio Companion, which is the import block. And here you can import anything you want from Python. So from math, I can import pi, and this will bring me the value of pi. And then what happens? Not sure. I'm going to set my maximum frequency limit and my minimum frequency limit. So plus 10 kilohertz and minus 10 kilohertz, and I did something wrong with the import. I'm missing a T. So now I have these numbers in radians per hertz, radians per sample. Sorry, I don't care too much about them. And let's play and run this. So I can see the output and the input of the PLL are very similar. The input is in blue, the output is in red, and the main difference is, well, the carrier of the original signal was 3 kilohertz away from the center because tuning was not perfect, and the PLL is managing to move this to 0 hertz. So this is what we mean by a PLL locking onto the signal and performing carrier recovery. We can close this and show you something else which is interesting. I'm going to put another GUI frequency sink and then separate this complex signal into its real part and imaginary part. And this can be done by the block complex to float. I need to change these from complex to float. And now I can play. And the interesting part, you see, in blue I have the real part, and in red I have the imaginary part. So it happens that the blue part has all of the residual carrier, and the red part has all of the data modulation we are interested in. Why is it so? Let's go back to the slides and try to discover it. So the reason is like this. Also, probably Mike is saying a throttle block would be appropriate. Maybe also not share my camera. I think it's putting too much load onto the computer. So the phase modulation works by going up and down through the unit circle. A bit 1 is transmitted by going here, and a bit -1 or 0 is transmitted by going there. And if we move along this black line, this is not so different from moving up and down like this. So this is the real, the actual phase modulation. This is just an approximation, which looks like quadrature modulation. Here we have a constant, which is the suppressed carrier and only appears in the real part. And we also have an imaginary part, which goes up and down with the data. So this is a very nice way to check that your PLL lock is working. You should get the suppressed carrier on the real part and the data on the imaginary part. This approximation actually comes from this formula, which is Taylor's theorem. Now the idea is we have 2 sidebands in the data. We are going to select one of the sidebands, and this is done with a Hilbert filter, which what it does is to filter the positive frequencies. So we are going to remove the left sideband and only use the right sideband. We'll use the Hilbert filter to remove the, leave the right sideband in place. And then we are going to move it to baseband, which means move the right sideband to the center. You'll see what this looks like in GNU Radio. Remember that if we want to move in frequency, we can multiply by complex exponential, because multiplying by a complex exponential is the same as shifting in frequency. So in here, we'll multiply by an exponential of negative frequency to move this frequency down to 0. All right, let's go and come back again to GNU Radio Companion. The first thing we need to do is to take the complex argument. This will give us the phase modulation. So remember we said this modulation works by shifting the phase of the signal. With complex to arc, we can access the phase. By suggestion of Mike, I think I'm going to put a throttle block. What this does is to slow down the flow graph so that it doesn't choke all my CPU. Then the next thing I'm going to do is to show the spectrum of this, actually. So frequency sync. So that you can see the two sidebands I'm talking about. Maybe I need some averaging. Here you can see we have, it's the same as below. We have the right sideband and the left sideband. Our goal is only to select this sideband and move it to the center. So the way we do so is first with a Hilbert filter, which will remove the left sideband. And then I need to put this back to complex again. 4096. And as you see, what the Hilbert filter has done is to remove all the left sideband. We still have the right sideband here, and now we want to move it to the middle. To do so, we can multiply. So there's a block called multiply for that. And then we need a complex exponential that is called signal source inside GNU Radio. So in signal source, you can generate all the kinds of signals you want, triangle, sawtooth, etc., but also cosine, which means complex exponential. And here I'm going to put minus 500 kilohertz. Why? If we saw in the frequency plot, the center of the sideband is more or less around 500, or actually 550. I'm going to cheat a little bit since I know the answer. 550 kilohertz. That's more or less the center of the sideband. So by doing so, what I find is what was before on the right-hand side of the spectrum now has moved to the center. What was before at 550 kilohertz, now it's at 0 hertz. Why are we doing this? Well, the main reason is this signal we have now here looks like a BPSK signal, and we can process it like so. So let's close this. Go back again to the slides. And now I'm going to show a couple of simple reverse engineering techniques And probably I'll preload the pre-done flow graphs, not to spend so much time on these details. So the first question we may have is, well, the frequency of 550 kilohertz I use was just an eyeball estimated. Can we check the real carrier frequency of this BPSK signal? And yes, there is a very nifty little trick, which goes as follows. We have our BPSK signal, y of t, and mathematically it looks like this. So it's like a hump in the noise of the spectrum, as you have seen. It doesn't have any filters we can recognize. But we take the square. When we take the square, we get this exponential, which looks like a carrier. This is a peak in the spectrum. We can see and we can measure the frequency. And the frequency will be 2f, where f was the original frequency of the BPSK signal. And the rest of this, I don't care too much about it. It just looks like noise. There is nothing very specific about BPSK in this trick. The same would work for MPSK. So this is when you have multiple phase shift gain by computing the mth power instead of the power 2. And let's go and see how this looks like. I'm going to open the flow graph, as this will give me more time that I can spend in trying to go more slowly, as some people have been quite right to suggest. It's not too good to rush things. And then here I have the flow graph. So this is more or less as we left it. And what I'm doing here is to multiply the signal by itself. So I use a multiply block to square the signal. And for the time being, let's disable this and run. And here you see this is at frequency 0. This is because this is the solution. So I have already the correct frequency here. If I put 550 as before, and here I'm doing multiply conjugate, which is the same as putting a minus in the frequency. You'll see this has a frequency error. So instead of getting this carrier at 0 hertz, we get it at 11 kilohertz. So this means our frequency error is 11 kilohertz. There's a question about how do I get rid of spinning arrows to see the GNU Radio design. It should pop up, so the shared screen should pop up for you. At least it's popping up for me. Maybe it's slow to pop up for you. And there's another question of how to pick the number of taps for the Hilbert filter. Usually the default of 65 taps works good. If you put more taps, it will use more CPU, but you'll get nicer filtering. So sharper edges on your filter. So in this way, you can see the frequency error you are doing here and actually replace by the correct number, which is 5555 hertz. The thing I have in the bottom, I don't want to take much time to explain it, is, well, in this GUI frequency sync, I don't have too much frequency resolution to see small frequency variations. Maybe I'm mistuned by just 10 hertz or something like that. So how can I know? Well, my suggestion is, since this signal here is already at baseband, so near 0 hertz, you can do a low-pass filter and decimate by 100. This will increase your frequency resolution in 100 times. And here, instead of seeing 2 megahertz of spectrum, you'll be able to see only the 20 central kilohertz. So you'll be able to see much better frequency resolution. So this is the way we are able to find the carrier frequency of any BPSK signal, which is quite important to tune to it accurately. And in the continuation, I will assume we are accurately tuned in frequency. Let's come back and discuss about how to find the symbol rate. The symbol rate is the speed at which these plus ones and minus ones are sent. And there's a very little trick to find this symbol rate. Here is the math, but you need not to look at it much. The key is y of n is our original signal. We are going to take y of n, delay it one sample, and then do the complex conjugate and multiply. There's a very good question about if it is possible to track the frequency adaptively on runtime. So yes, this is possible. This is done either by an FLL. There's a bandpass FLL in GNU Radio, and it is also possible by doing a Costas loop, which we'll get to in a few slides. And also Schneider is suggesting this is sensitive to the sample rate of the SDR. Yes, it depends a little bit on the sample rate of the SDR, but it doesn't matter a lot. In fact, the choice of one here is arbitrary. You could do a different delay and it would still work. The idea here is that often y of n and y of n minus 1 lie on the same symbol. So when you multiply, then here you get a real and positive number. But when y of n and y of n minus 1 lie on different symbols, say this is a plus 1, this is the symbol before, which was a minus 1, then we have plus 1 times minus 1, which is, it will give you a minus sign. So what this signal Zn looks like is a sequence of pulses which occur on some of the symbol transitions. And by looking at the spectrum of Zn, we can see where this characteristic frequency about the symbol rate happens. And this very simple trick comes from cyclostationary analysis, which is a very powerful theory and tool we can use to explore many different aspects of modulations. Let's move on to the flow graph. Hopefully the shared screen will load fast for everyone. And then open the symbol rate. All right, so here what we have is, well, I need a delay of 1. Surely I didn't check. So we have our original signal in here. We delayed one sample, then multiply the original signal against the complex conjugate, and then we do an FFT. And what we're going to do is to play this, and this is the spectrum. We see something at 0 hertz, this is normal, but also at 555 kilohertz, we see the spike produced by the symbol rate. So the symbol rate is actually 555 kilohertz. Oh, I have closed my radio session. Sorry, probably can restore it real quick. Okay, there we go again. Sorry, I'm using kind of a slightly complex setup to share the screen, so I closed it accidentally. So yes, the analysis for the symbol rate shows that the symbol rate is 555,555. This is the same as the frequency we had here, and this is not surprising. It is because in Manchester modulation, the subcarrier frequency and the symbol rate are the same, as I already explained in one of the previous slides. And here I have the same trick as before to get more resolution on the frequency measurement. But since now the frequency of interest is not centered at 0 Hertz, but rather at 555.555 kilohertz, we do a frequency translating FIR filter, which is like the low-pass filter, but first it moves a particular frequency, in this case this one, to baseband, and then it decimates. All right, so let's go back to the slides and get onto something more interesting, which applies to most digital modulations out there. Now the signal we have, if we look at it in the time domain, looks like this picture. It has plus ones for the 1 bits. It has minus ones for the minus 1 bits, but it's really noisy. So we want to do two things. First, we need a matched filter to remove this noise. And then we need to find the optimal sampling locations for the symbol. These are shown here in red. This is where to read. This is 1, 1, 0, 0, row of ones, couple of zeros, 1, 0, etc. The way to do this in GNU Radio, the matched filtering is easy. We can use an FIR filter for this. And since here the pulse shape is just a square wave, the matched filter will be a square wave, which means a moving average. For the optimal sampling locations, we can use one of the symbol synchronization blocks in GNU Radio, for example, the symbol sync block. And Andy Walls, who made this block, has a very nice talk in GRCon 2017, completely devoted to this symbol sync block. So I suggest that talk for more details. Another thing we want to do is still we have a small frequency error on our signal. What we're going to do to correct for that frequency error is to use a Costas loop. So the Costas loop is similar to the PLL, but the difference is PLL will work on a carrier, on a signal which has a spike on the spectrum. And a Costas loop is designed to work with PSK modulations, which has data changing +1, -1. And there is a small particularity about the Costas loop, which is there is a 180 degrees phase ambiguity. This means that at the outputs of the Costas loop, we may get the signal of symbols we intended, or either minus the signal of symbols, so everything inverted. And we need to take care and to take that into account. And a very small remark is that here we are actually using the Costas loop to recover the Manchester subcarrier, because the carrier, the main carrier of the signal, was recovered by the PLL in the first step. So this I think I can do for real. It's probably one of the important steps. So let's maybe disable that, throw this away. We can disable blocks in GNU Radio Companion by pressing D. And then I need some variables. So I'm going to define the baud rate as this 555, etc. And then it's very useful to have a variable called samples per symbol, or SPS, which is the baud rate divided, the sample rate divided by baud rate. And I see a good question in there. Does the Costas loop replace the signal squaring block? Kind of, yes. Actually, the Costas loop inside does some kind of squaring of the signal. So the two techniques are very much related. So let's go and put decimating FIR filter. And then here, I want to have just ones, as many ones as samples per symbol. Okay, the samples per symbol is 3.6. I cannot have a vector with 3.6 ones. The best I can aim is to have 111. I'm dividing over 3 for normalization, but this is okay. And what is the problem here? Yes, this needs GNU Radio, Python vector. So maybe it's easier to do in NumPy. Said I can import anything I want, and in some of these flow graphs I'm using NumPy. It's typical to import NumPy as MP. So here I have my vector of 3 ones, or rather 3 1/3. This will perform the matched filtering on the signal and reduce noise. And then the symbol sync. So symbol sync has a large number of parameters. As said, this requires the full talk to explain. Here I'm going to use the Gardner time error detection. We already have our samples per symbol variable. The loop bandwidth is the same as PLL loop bandwidth. It sets the speed of response of the system. Here the signal is very stable, so I can use a really small loop bandwidth. And here maximum deviation also sets how much deviation from the nominal samples per symbol is going to try this block to achieve. So let's go and put Constellation sync. The Constellation sync will display the symbols as dots on the screen. So I can run this, and hopefully you'll be able to see a couple of dots, but they are rotating. And the reason they are rotating, I'll close this right away, not to shutter too much the audio, is because we haven't done the Costas loop. So Costas loop will correct for that rotation in phase. Again, we have bandwidth. Everything which has bandwidth on it has a loop bandwidth, which needs to be tuned to the specifics. I see a couple questions. One is the FIR filter decimated moving average? It's actually not decimated. If you look here, I use decimation 1, so it's just a simple moving average, no decimation. The reason I'm using the decimating block is because there is no FIR filter block inside GNU Radio. There is either decimating block or interpolating block, but we can use any of those with decimation or interpolation equal to 1 to achieve a simple FIR filter. And I think that's pretty much the question. So the order here of the Costas loop, we need to set to 2. 2 means BPSK. For QPSK, we would set it to 4, etc. And now if I play this, I can see my constellation is this blob of dots, which is the symbol -1, this blob of dots, which is the symbol +1. And one thing to notice, the symbols are not really centered at 1. They are centered at 1.16 or something. This is because of the deviation. We didn't correct for the deviation. If we want, we can divide here by 1.2 or whatever we need. And then we can try to drive these blobs towards 1. Actually, the amplitude we need to correct is 1.6. So by putting there 1.6, we have nice symbols centered at +1 and -1. All right. Another thing which is good to use, but this I'm going to probably fetch it from here, is the Qt-GUI timesync. The Qt-GUI timesync, which we will be using, lets us see the symbols like so. Let me insert the throttle block. And then we have in time the symbols +1s, -1s, and we see that there is a nice separation between +1 and -1, the same as in here. This means there are very few bit errors. So this is good. This is because this signal was quite strong. And now let's come back to the slides. Okay, so now we have the symbols. The symbols look just as you saw, as a continuous stream of +1s, -1s. What do we do with them? Well, there are a number of standard protocols which are used in deep space communications and also many other kinds of space communications, which are called CCSDS protocols. They are standardized by a committee, and they are described in the blue books. So if you search online for CCSDS blue books, you will see there are a number of documents describing the standards. One of the most important for this talk is the TM synchronization and channel coding blue book. This describes a number of things we are interested in. The error correction, so these are algorithms used to encode the message so that the receiver can detect and correct bit errors. The scrambling, this is used to make the message, the transmitted message, look random, but this isn't used for encryption or obscurity or anything like that. It is done for performance. There's a very nice quote I like from Phil Karn, which is that any advanced enough form of communication is indistinguishable from noise. And this is quite true. The more your modulation and data looks like random noise, the better many signal processing algorithms and techniques work. So this scrambling is done to make the message look random, just because of this reason that Phil Karn says about these noise-like signals. And the third important thing is the sync word. Sync words are small sequences of bits which are used to mark the beginning of frames. There is an attendee who is seeing a white screen. Is like that for everyone? I guess not. So let's say we have a 32-bit sync word. That means that before every message, we use the same 32-bit fixed string of bits. So this is used by the receiver to detect where the frames begin, rather than be looking at a continuous stream of never-ending data. There are a different number of error correction algorithms used in the CCS Blue Books, and these are the following. There are convolutional codes, which are better known by the decoder, which is called Viterbi decoder. And you have a couple of Viterbi decoders inside GNU Radio. There are Reed-Solomon error correction algorithms also. You have a Reed-Solomon decoder in GNU Radio, and also another one in GR satellites. There is concatenated error correction, which is a combination of convolutional encoding and Reed-Solomon. The transmitter does Reed-Solomon first and convolutional encoding second. So the receiver must do convolutional decoding first and then Reed-Solomon decoding. There are turbo codes and LDPC codes, and these are state-of-the-art error correction codes, which are able to perform very well with respect to the data transmission theory of Shannon, the Shannon limits and things like that. So how can we guess what is the fourth error correction method used by our solar orbited signal we are working with here? Well, there is a nice trick, which is to look at the sync word. And luckily, the sync word that is used in each of the fourth error correction methods is different, as shown by this table, which comes straight from the Blue Book. So in a large number of error correction techniques, we have this 32-bit sync word, but for some of the LDPCs, and actually for some of the turbo codes, we have different sync words. By trying to search for each of these in our data and getting a match, for example, in our case, we'll be able to find this sync word. We can identify which is the correct error correction code to use. The only thing to take note is that with convolutional codes, this sync word is not sent in the clear. It's actually sent encoded. If you know anything about convolutional codes, this is like a continuous encoder where you put all your information, including the sync word. So the receiver has to do continuous decoding, continuous Viterbi decoding, and then it can look for the sync word in the output of the Viterbi decoder. For the rest of the error correction schemes, it's the other way around. The receiver first searches for the sync word in the data, and then it can know where the frames start, and then it can push those frames to the error correction decoder. So we are going to use correlation to find this sync word, actually. And the way we correlate is, again, using the decimating FIR filter block. Let's go ahead and move on to this slide, sorry, the flow graph, which I'm going to open because, as you'll see, to save me from typing here, I have some variables with the data already loaded. This is a sync word in hexadecimal. Just copy it straight away from the Blue Book document. This is the sync word as a sequence of bits, so -1s and +1s. We could go and compute this by hand, but here I have preferred to use a rather convoluted NumPy thing to get the string in hex, decode it, then unpack the bits, and grab and transform those as -1s and +1s. For further reference, you have these with the workshop material. So this is just the thing where we're looking for -1s and +1s. And then we'll also need the same thing, but as a string of 0s and 1s, because there is a block from GNU Radio which expects this kind of format for the sync word. So, okay, this is more or less the flow graph as we left it. I'm going to copy and paste the throttle block in case it's been any help with the audio. And then what is new here? Well, we have our symbols. This complex to real, I didn't comment about it in the last flow graph. The reason we are doing this is because a BPSK modulation lies only on the real part of the signal. So we just get the BPSK modulation by passing to the real part. For QPSK modulation, we would get the real part, we would get the imaginary part, and we would have some of the bits in the real part, some of the bits in the imaginary part. I see a question here is, can samples per symbol being non-integer, such as in here, 3.6, be an issue? That's a really good question. So this is an issue here. I'm not doing the correct matched filter. I'm doing an approximation. I'm only using three samples to average instead of 3.6. So a fractional resampling could be used to arrive to samples per symbol which is integer or close to integer, and then this filter would be better. But it is good enough for us. And then when working with the symbol sync block, no, you don't need any sort of integer number here. It can work correctly with any samples per symbol you can think of. And M&M, which is the Mueller and Mueller block, is a very popular block. And you shouldn't use it actually, because all the functionality about Mueller and Mueller is contained in here. And this block fixes a few bugs of the old Mueller and Mueller block, but it doesn't need an integer samples per symbol either. So I think it's only helpful when you're doing things like this. Then we have the symbols here. We are correlating, and correlating is the same as doing a matched filter against the sync word, but we have this funny looking colon -1. In Python, this means revert the order of the sequence. So just turn it around. The first element becomes the last one, etc. This is done because to correlate with an FIR filter, you need to reverse your thing you're trying to correlate with. The mathematical reason is an FIR filter performs convolution. We are wanting to do correlation. Correlation and convolution are quite related, but there's a reversal in the middle. So don't forget to reverse your sync word. Here I'm also dividing by the sync word size to keep things normalized. So here sync word size is 64. And this is so that I'm throwing in +1s and -1s. The sum of the absolute values of all of these is going to be 1. So the maximum value I'm going to have at the output is +1. So that's the reason of the normalization, to have +1 or -1, because we have this plus or minus ambiguity of the Costas loop. And here we have the GUI time sync. The only novel thing is I'm using 100,000 symbols just because the packets are very long. So in this way, we are able to see several frames inside the window. So let's run and let's stop. I actually have a trigger. So I went to more involved things in the supplied flow graph and put a trigger to trigger on this sync word, but it's not necessary. We have the sync word displayed here. Here it is in red. I'm trying to zoom on it. So by seeing here, the correlation looks like -1 and the rest is just noise or no correlation. We see that we have one correlation here, one correlation there, etc. So this is a frame, and this is the start of the frame, and so on. So, okay, let's go back. I think it's time for me to go back to the slides. And let's see what we have ahead. Okay, now we know where the frames start, but there is another important thing about, we also know that these are turbo codes, because the sync word we were able to find is only used for turbo codes of a particular rate, which is rate 1/2. And that's very nice, but there are a number of different sizes for these turbo codes. And this table 6.2 is again taken from the Blue Book straight away with the sizes of the different frame sizes. There is more detail in the Blue Book, but the thing this works is this is the number of symbols transmitted. So this is symbols which include overhead due to error correction. The way that error correction works is to send redundant symbols. So we are always sending many more symbols than the size of the original message. In fact, rather 1/2 means roughly we send twice as many symbols as the size of our original message. So this is the number of symbols we are expecting to receive. In here, you can see it's almost half of what we have here. This is the size of the original message. So, okay, we are dealing with symbols yet. So we are trying to find one of these lengths, and we take advantage here of the fact that frames are transmitted back to back. The way it's done is we have the sync word for one frame, then we have the contents of the frame. Going to spoil a little bit and tell you that this is the correct size. So then we have 17,000 symbols following the sync word, and then the next frame begins with the next sync word. So the idea is to find the distance between sync words to be able to find that this is actually 17,000 and not 14,000 or 3,500. And then from this to be able to guess the frame size. For this, we are going to use two GNU Radio blocks. The first one is called Correlate Access Code Tag. This is done to, so what this block does is to find the sync word. It can allow a certain number of bits to be wrong in the sync word, but other than these bit errors, it will look that the sequence looks exactly like the sync word we're searching. And whenever it sees a sync word, it will detect the sync word and add a tag. Tags are objects used inside GNU Radio to add metadata to a running string of symbols such that we can mark any number of things. Where words begin, what is the current time, what is the frequency we're tuned to, and many other things. We want to attach information to a particular sample. We do that with a tag. And there is also the tag debug block, which can be used to print tags. And one of the things it prints about tags is the location in which sample in the stream they happen. And since here we are working with symbols, after doing symbol sync, Costas loop, etc., the distance in the locations of the tags as printed out by tag debug will be the distance in symbols between the sync words. So let's go and do that inside GNU Radio Companion, and I'm already loading for you. Flow graph number 8 for the frame size. So the novelty here is we have inserted this correlate access code tag. Here we are using the access code variable. Threshold is the number of bit errors we want to allow in our sync word detection. So we allow up to 4 bits to be incorrect. And this is useful when dealing with noisy signals. Never impose that your sync word is 100% correct. leave a chance for a few bit errors. Don't put too many bit errors here, because then you will do false detections. You'll trigger on things which are not the correct sync word, but do leave a small amount for error. And then we need a name for the tag that is going to be inserted by correlate access tag. And this is going to be called sync word. As I said, we are not sure if we are looking at our original stream of data or at the stream of data multiplied by -1, because the particularities of the Costas loop. So we run two decoding chains in parallel. One of them will succeed and the other one will fail. In the first one, we consider the stream of data is okay. In the second one, we consider the stream of data needs to be inverted. And this we do by multiplying by -1 with this multiply const block. Actually, the way this flow graph has locked on the Costas loop, we already saw on the previous flow graph, is through the -1 branch. We saw that correlations were negative. But this could change anytime if you run with another recording, if you run with different parameters. So always treat both cases in parallel. And then tag debug doesn't have anything fancy. I've set it to 2 inputs because I have, well, 2 streams of data. I'm filtering it to only log on tags which are called sync word. And this is going to display some data about the sync word. All right, so small note about this. By default, when running these flow graphs, GNU Radio Companion will print information here. This is not very efficient. This tag debug is going to generate a lot of messages to print here. So it's better to run it on the terminal, like here, so as not to hang up GNU Radio Companion with all these messages. As you may know, when you hit this generate button on GNU Radio Companion, it will generate a Python script for you that then you can run from anywhere. So this is what I'm doing here, but this is number 8, what I need. Yes, sorry, I need number 8. So let's run number 8 and stop it really quick. And as you can see, there are these sync word details printed by the tag debug message. It says the name of the tag is sync word, some other data. Here we are interested in the offset, but before, is it possible to have false positive in the sync word detection? This is a question. Yes, it is. If you use a larger threshold, you'll definitely get false positives. So do adjust your threshold to get a reasonable amount of false positives, especially if sync words are very, very short, then it's quite likely to get false positives. With a 16-bit sync word, for example, even if you don't allow any bit error, you will still get false positives. So yes, this is not foolproof. You can come up with better schemes which log only once and then expect that the next frame will start at the appropriate location after the second frame, or where you need to detect several sync words in a row. But none of this is 100% foolproof. Okay, so coming back to these offsets, what we want to do is subtract these two. And I can do this in Python. And this will tell me the distance between the beginnings of two consecutive sync words. This is 7,912. This is pretty close to the number we had on the table taken from the Blue Book, but not exactly the same. Why not? The numbers on the table from the Blue Book measure only the symbols inside the frame. They don't measure the length of the sync word. So here we need to subtract the length of the sync word, which is 64 bits, and then we get 7,848 symbols per frame. This matches the table on the CCSDS Blue Book. So now we are completely sure that the for error correction is turbo code with the largest possible frame size. All right, let's get back to the slides. Now we want to do turbo decoding. So how turbo codes work is quite interesting, but of course there's not any time to go into the details here. I'll just mention that here we are using an implementation done by Gianluca Marcon for a university course project in 2017. He was quite nice to publish his implementation as open source code. So in fact, this was used later. Wei Minchuan from Harbin Institute of Technology in China took Gianluca's implementation and incorporated it in some GNU Radio blocks inside this larger GR-DSLWP out of 3 module. This was used during the Longyan 2 Chinese lunar microsatellite mission, which ended on August last year. This was a Chinese microsatellite using turbo codes and amateur radio bands and GNU Radio on the decoder, and we used the Dwingelo telescope in the Netherlands to receive and decode the telemetry. So all of the ground station was done in GNU Radio, and there's actually a paper published about it, so you can look about that if you're interested. This out-of-stream module was done originally for GNU Radio 3.7. Here I have ported the out-of-stream module to 3.8 just because I wanted to use turbo decoding for this talk and for other projects. Keep in mind that I'm pretty sure not all the full GR DSLWP is working on my 3.8 port. I need to go back at it and fix a few things. But the turbo decoding we are going to use here is working. We are going to use 3 different blocks from GR DSLWP, and these are the following. First, we have frame splitter F. This is very simple. It will find the tags we are already generating, marking the beginning of the frames, and it will extract each frame and put it in a PDU. PDUs are things which GNU Radio uses to pass asynchronously packets between different blocks. So far, we've been working with a continuous stream of samples. When we want to deal with packetized data, we use PDUs. The next block is the pseudo randomizer, which is used to perform descrambling, and the final block is the turbo decode for actual turbo decoding. Let's go on to GNU Radio. And as the screen loads, let's see if I can, yes, grab the turbo decoding flow graph. And as you can see, we'll resume where we left with finding sync words with correlate access code tag. And here we have the frame splitter F block. So there are the frame splitter blocks in GR DSLWP. The F is because floating point here. 2 parameters are important. The name of the tag we want to use a sync word. Here we are using sync word, but this needs to match the tag name here. And the frame length. This is the frame length we just found, which matches the frame length on the CCSDS table. So this will just wait for a sync word, take the 17,848 bits following, or rather symbols following the sync word, and output those as a PDU. We have two because we have two different decoding branches, but then since we're working with PDUs, we can mix everything in a single branch. The next thing we have is the pseudo randomizer. Here is also important to specify float bits as the format, because we have also for dealing with unpacked bits or packed bits. And here, let me see if I can scroll. Yes, we have the turbo decode. A few parameters are important. The base is always 2 to 3 unless you are doing something really non-standard. Octets sets the size of the frame. This is related to the 17,000 bits we are selecting, and the correspondence is detailed in the CCSDS Blue Book. The core rate 1/2 is also important. And here we have iterations. The more iterations we put in, the best the decoder will perform, but the slower it will be. And I need to remark that this turbo decoder is not very optimized. It doesn't use SIMD instructions, so it really runs slowly. This is not a problem for this post-processing as we are doing here with a recording, but on my computer, this is quite far from running real time with a high symbol rate signal such as this. So, all right. After we get the decoded PDUs, this is the way we store them to a file. We use PDU to takt stream to convert the PDUs to a stream of bytes. This will just put one PDU after another in a stream of bytes, and then we use a file sync where we can write wherever we want a file with the decoded frames. And since these are unsigned 8-bit numbers, I tend to use U8 for the extension, but you can use anything you want. You need to set the input type to byte. And as said, this doesn't run in real time. If you run it, you'll find that the graphical part of the decoder, this GUI sync, which shows the symbols and everything else, will finish at some point, but your CPU load will still be quite high because the turbo decoder has a large backlog of undecoded messages and is going through all of them. And only when you see that your CPU load goes down and your frames file stops growing, you can stop the flow graph. If you stop it when your GUI sync has stopped, then you still have a job to do at the turbo decoder. So in the interest of time, well, I see I have really quite some time, so yes, maybe I'll run this. I'll try running this. I was probably too far at the beginning. Now I'm back ahead on time. So if we run this, I'm not sure if my audio is going to go crazy, but I'll try. We get again the decoder GUI, and then probably it's better to do here. If we check upon our frames.u8, we can see it's growing size as the turbo decoder processes more and more frames. So let's close this and stop this. Let's see my jobs. All right. So let's go back to the slides. Now we have our frames file with decoded frames from the satellite. And here actually our work in GNU Radio Companion ends. But where else can we go from here? If we want to continue doing things with these frames, we can look at these blue books from CCSDS, which define the link layer protocols that are used. The two more important for transmissions from spacecraft to ground are the TM, which means telemetry, space data link, and the AOS, space data link. AOS means advanced whatever. There is also the TC space data link. TC means telecommand, and this is used from ground to space. So by reading these documents, there is a lot of architecture inside the documents, but if you skip to the interesting parts, and I will show some of these, you can see how these TM and AOS protocols work, and you can check what of these are used in your frames and do something useful about them. For example, we haven't checked that our decoded frames are correct. Many of the error correction algorithms, including turbo codes, will always succeed. If we feed in a good signal with maybe some bit errors, they will output the correct decoded frames. But however, if we feed in a signal with lots of errors or maybe even garbage, random noise, they will also output complete garbage. This follows the principle garbage in, garbage out. So with all these forward error correction algorithms, we need to check that the output is okay. The way this is done in CCSDS protocols is by inserting a CRC16 at the end of the frame. So the specification for the CRC is in the blue book, and you can implement your own. I think there is one that would work inside your satellites, and I'm going to show one done in Python in a moment. An exception to this, if you're working with Reed-Solomon frames, Reed-Solomon frames don't always succeed. They tend to fail when the number of errors is large. So they can be used as a built-in error correction scheme, error detection scheme, and it is useful not to include a CRC16 with Reed-Solomon. So I said no. We have these TM and AOS protocols as the link layer, but what do we have at the upper layers? At the upper layers, either we have some custom ad hoc protocols designed specifically for the mission, or we have space packets, which is a nice way to fragment datagrams or packets. Maybe think about it like IP fragmentation in the internet stack of protocols, but also to distinguish between different applications. So think of the concept of port like in TCP or UDP ports, which are used to separate the data for different applications. So many times space packets are used on top of TM or AOS space data link. And typically, when I get my frames from GNU Radio into a file, as I've shown, what I'll do is to launch up a Jupyter notebook and try to see in Python things about these protocols to try to extract the information, see if I can recognize anything about the data, etc. I'm going to show an example about this, but I want to mention that probably we can also, in this case, use the nice CCSDS blocks included in GR satellites. This was made by Athanasios Theocharis, a student from Thessaloniki University in Greece, during last year in ESA Summer of Code in Space, which is kind of similar to Google Summer of Code, but sponsored by ESA, and all projects need to have some relation to space. In our case, Solar Orbiter uses TM space data link frames. There is the remark that LDPC codes can also do error checking. Probably, I'm not really sure. I'm not so familiar with LDPC codes. I think it would depend on the algorithm you use to decode the LDPC codes. Most of the good ones are based on probability on message passing algorithms, and they kind of estimate what was the most likely message that was transmitted. So they will always tend to give you some message, even if it's garbage, but maybe you can turn it into an error checking scheme as well. So coming back to the TM frames, this is one of the good parts of the Blue Book. This is the things you need to look for if you're just doing a quick read of the Blue Books. Tables where you have the frame structure, the fields, how many bits, what is the meaning of each field. So this is the header, the number of bits, and the name of each of the frames. And there is a trick to distinguish between TM space data link and AOS space data link, which is that this first field is the same for both. The structure for the remaining fields is different, but this is the same for both. And the value will be different. I think a value 00 marks TM here, and 01 marks AOS. So that's a small hint for you. And then let's try to look at this Jupyter notebook with the CRC and the TM headers. Let's see how can I run this properly. I have some run Firefox script here, which I hope will, yes, perfect. So with the workshop material, you have these frames, Jupyter notebook. You can click on kernel restart and run all to evaluate all these cells. The way Jupyter notebook works is by typing in a Python code or code from another programming language into these cells, and then you will evaluate cell by cell, and the output of the cell will be printed below the cell. And you can also do inline documentation, type markdown, and things like that, and inline plots and so on. So this is intended as something you can carry with you to home and to serve you as a basis for further analysis, if you will. This shows you how to open the frames. Here we use the frame size in bytes. And here we check, we have decoded 1,656 frames. This is from a previous run I did, where I let the decoder run until completion of the turbo decoder. This is my quick and dirty implementation of the CRC16 codes, and you have a link to a very useful online calculator. So nothing special. Here we check what frames have valid CRC, and we find 2 frames have invalid CRC, and the others have valid CRC. Then it's very useful to print the data as an image, the bytes in the messages. So each packet would be a row, and then each column represents a byte within the data, and the bytes are color-coded. So in fact, this is maybe too small to see, not sure if I can zoom in, it seems not, but maybe on the left column you can see the headers. There are some counters, which count the number of frames. We'll see this in a moment. And you can see there are different textures. So this is because there are different kinds of data being transmitted by the spacecraft. And this already can give you some indications about what to look if you want to delve any further and grab some really useful data from the spacecraft telemetry. And in some lucky cases, this is actually possible. You can look at this and scratch your head and come up with some meaning and interpret some of the data and do something useful with that. So something else you can do, there is a nice Python package which is called construct. It can be used to define binary structures. Like here, this field has 2 bits and it's an integer. This one has 10 bits, etc. And then it will automatically parse and build, so both decode and encode these binary structures for you. So we can use this to parse the TM primary headers in the TM space data link protocol. These very few bytes at the start of the packet. And we can, for instance, print the contents. So here you can see the transfer frame version number is 0. As I said, this indicates the protocol between TM and AOS. You can also see the spacecraft ID. So different spacecrafts will use a different ID. I think of this as an IP address. You can see virtual channels, which are used to separate different applications, different kinds of data. You can see master channel frame count, which is a frame counter that keeps increasing with every frame. This is used by the decoder to check for missing frames. So here you can see the first frame has a 6, then 7, then 8. Each virtual channel has also its own private frame counter. So this is called virtual channel frame counter. And there are a number of further flags and fields. You might look into the Blue Book documentation. We can classify by virtual channel and count how many packets are in each of these virtual channels. So we see most of the packets are in virtual channel number 2, but we have a few on virtual channel 0 and 4. And maybe it's a good idea to look first at these two because there are data which is not transmitted very often. Maybe there's something interesting which we can figure out easily. But also look at virtual channel number 2 because sometimes just by looking at a sheer large amount of data, you can figure out patterns which might be not obvious in less frames. We can plot the values of the frame counter. As you see, it goes from 0 to 255 because this is an 8-bit counter and then rolls over. And this can be taking correct care of the rollover to detect the number of packets lost, so 0 packets lost. Then we see that these 2 frames with invalid CRC are maybe false sync word detections, or maybe right at the beginning of the data, right at the end. I'm not sure. It's not so difficult to look at it in more detail and see where these 2 invalid frames come. So this is the kind of things I tend to do in Jupyter Notebook, which for me it's great for prototyping. The thing that is great for, with GNU Radio and GNU Radio Companion is to build streaming things that grab data, process it. You can have a very, very large recording, and GNU Radio will keep reading from it. It will not read it completely in your RAM. And that is very useful for many things. But if you want to have a static vision of the data, maybe do some post-processing analysis, correlate some things, try to find patterns in the data, I think it's better to investigate and prototype within Python or any other language, which lets to look at plot really quickly all the data at once. And then your guesses, your findings, you can turn those into GNU Radio. And using the built-in GNU Radio Python block, this can be as easy as maybe copying over code you first designed in IPython or in Jupyter or somewhere else. So let's go back to the slides for the final things. I'm actually reaching the more or less the end of the workshop. So about Bepi Colombo, there were 2 recordings supplied with the workshop material. We've only worked so far with Solar Orbiter. Bepi Colombo is very similar to Solar Orbiter. Here you have the parameters for both spacecraft, and the only difference is the baud rate. Both use Manchester coding, the same frame size, turbo frames, rate 1/2, the same TM protocol, etc. The interesting thing about the Bepi Colombo recording is that since the spacecraft was farther away from Earth, the recording is much weaker than Solar Orbiter's. So it's a very good exercise to grab your Solar Orbiter decoding, load the Bepi Colombo recording on it. Of course, change the baud rate and the subcarrier rate for the Manchester parameters to match with Bepi Colombo. And then see if it still works, see if it decodes correctly. Because where I was a bit careless with the parameters I use for the PLL block, for the symbol sync, for the Costas loop, because the Solar Orbiter signal is actually quite great. It has very good SNR. Bepi Colombo pushes things further, and you need really correct choices for all those parameters. So good exercise, as I said. Not sure what there is on Solar Orbiter telemetry. On Bepi Colombo, most of the telemetry contains idle data, which is just when what a spacecraft would transmit when it doesn't have anything noteworthy to say, but it still wants to keep the transmitter running to make the signal visible and trackable from the ground station. But anyhow, this idle data is quite interesting to analyze because it's filled with a PN sequence, so a pseudo-random repeating sequence that nevertheless resets at some rather unexpected and interesting points. What else? Further reading. If you're interested in these kinds of things, I've done quite a lot recently. Actually, this workshop abstract was submitted, I'm not sure, maybe around June or May, but in July, 3 different spacecraft, Emirates Mars mission from the United Arab Emirates, sorry, Tianwen-1 from China, and Mars 2020 from the US have been launched to Mars, taking advantage of the Earth to Mars launch window. And in collaboration with Paul Marsh, with other radio amateurs, and with AMSAT DL, the Radio Amateur Satellite Association, and Bochum Observatory, where they have a 20-meter antenna, which is really good to receive these weak signals. We have been able to do this kind of GNU radio decoder work for all of these spacecraft, all of these signals. And the question by Rohan is, any thoughts on the data of these frames? No clue about a Solar Orbiter, as I said. With what I learned with these spacecraft, I need at some point to go back to Solar Orbiter and take a closer look at the data, because at that time in February, I think, I wasn't able to figure out much about it. But I think there's some data, and maybe we can pull things. On this spacecraft, yes. So for Tianwen-1, we've been able to find lots of telemetry variables. We are actually able to make sense of the ADCS system to know where the spacecraft is pointing in real time, to know where the spacecraft is in real time, because this spacecraft has something rather unusual. It also broadcasts its orbit information, and we are able to find a number of things. And Bochum is tracking Tianwen-1 each day and gathering lots and lots of data. If you just go to my blog and just read the latest post or search about this spacecraft, you'll see the kind of things we're doing. What else? Nothing else. I had some additional material, and this was mainly intended in case I had lots and lots of remaining time. What this is about is, well, we've seen here one approach of decoding Manchester modulation, which is used in many other contexts besides deep spacecraft. For example, for any radio amateurs out there, the Q100, the geostationary satellite for amateur radio, uses Manchester encoding on its amateur beacon. So we've seen just one approach to decoding Manchester modulation. Here I wanted to leave you two other approaches that are interested for Manchester demodulation. I'm not going to explain them now. I think it's better to do a wrap-up and do some comments or questions from you. And if you happen to be interested in these techniques of Manchester demodulation, you can always look at the slides. I'm going to be available on the chat throughout the conference. So just message me on the chat, or my email can be easily found online. Drop me a message and we can talk. So probably giving you the microphone for questions, comments. Probably I went too fast at the beginning. I don't know if there's something I should cover in more detail. Okay, I see there's a couple questions. Is there a GCC generalized cross correlator block in GR for low SNR sync detection? I think I'm not sure what generalized cross correlator is. So maybe if you can explain about generalized cross correlator, I'll be able to answer that more accurately. For just normal cross correlation, you can do using an FIR filter, as I showed, but this is not optimal. This is O of n squared for anyone which knows the big O notation. You can do with O n log n by taking advantage of Fourier transforms. So you can Fourier transform your data, you can Fourier transform your synquot, and you can multiply the Fourier transforms, do Fourier transform inverse. So maybe those who know to do cross correlation on the frequency domain know what I'm talking about. If you don't, I think there's plenty of material out there. GCC's Hannah Thompson frequency domain cross correlation. Still not sure what is it. Probably you can do your own. So it's not built in, but building on top of the FFT blocks and the vector multiply and so on, probably you might be able to do your own. What are you working on now for the future? So plenty of things. Ben mentioned in the introduction talk my GR satellites project. This is the thing I devote most of my GNU Radio time, so to say. And here we only use the AGC block, but GR satellites has full collection of decoders for amateur satellites. You can see my talk about it last year in GRCon. I'm also working further with the data from Tiangong-1. We are actually expecting to be able to detect correction burn on some time on September. We don't know when. The amazing part of this mission is the Chinese don't make a lot of public press release about when they are going to make maneuvers and things. So by tracking the spacecraft, we are actually able to detect this in real time. So this is like my continuation for the work shown here, and I'm also involved with many other side projects on DSP. And here Maitland is talking about who wants GR satellites in Debian. I think I wanted actually using Debian for the build route, so the continuous integration of GR satellites, Debian testing, and it works great. Would it make sense to have a Debian package for GR satellites? Probably yes, but this is something I kind of talked with Maitland last year at GRCon. Maybe not in Debian stable, because the problem with GR satellites is, look, these people keep launching new and new satellites. So I keep updating GR satellites to keep track of what everyone is doing, launching new birds. So typically there is an update every month or every couple months to GR satellites. In Debian stable, it would get outdated real fast. But having it as a side repository, some people are suggesting underboning, or just having it as a download in GitHub. I think that would be really interesting, and I'm looking forward to doing that myself, to bothering Maitland with any questions or issues I might run into. And yes, another question: has anyone tried tracking Mars? So MOM orbiter mission, this Mars orbiter mission, I think, from India. I'm not sure, maybe not. With a 2.4 meter dish you have, I think you should be able to detect a faint trace on the spectrum. So this is something I said at the beginning. This kind of data demodulation, where we are able to run fault error correction to grab the bits to see the data, needs a lot of SNR. You need the 20 meter dish at Bochum to be able to do it from Mars. And the thanks for the amazing virtual machine should go actually for the GNU Radio team, the project officers, and actually Bastian Blossel, who was kind enough to do a modified virtual machine with the stuff for this workshop inside. Are there more files if we don't have a dish? Yes, there are a few of them. Maybe I need to do a comprehensive list. There are some further recordings that Paul Marsh has published. There are some from Viljo in Estonia, I think. They have a large dish in the university. So I might point you to that if you're interested. Probably I'll add a comment to the README on the workshop material with more links. And there is lots of recording material done on Bochum. Unfortunately, it's not easier to publish those due to internal policy, so to speak. So yes, sharing this is well, they tend to be large because the sample rate is usually large, and also policy about who recorded the signal. Is this friendly enough? Is this considered spying on someone else's satellite? So there are always these kind of things, but even there is some very interesting recording from 5 years ago. I think I might point you, which was done in Green Bank Observatory by Breakthrough Listen, which is a project from SETI. Since we are celebrating this year that SETI and GNU Radio are joining forces, I think it would be really interesting to go grab that IQ recording, which is a recording of Voyager, not sure if it's 1 or 2, with the rather large dish at Greenbank. Steve Croft is saying maybe more new captures for everyone from Allen's telescope array, Voyager 1. So yes, through this collaboration with SETI, maybe we can have more data available to us, just to play around with it and to learn and see. So looking forward to that with Steve Croft and the rest of the SETI members. I'm not sure if I skipped any other questions. For the parameters. So the correct parameters of the previous slide, I don't recall anymore what was the previous slide when the question was made. But for guessing the correct parameters, you have them at the GRC files in the workshop material. And here I've tried to, especially at the beginning where I was working building the follow graph live, I tried to show how I really work in practice with an unknown signal. Of course, it's impossible to condense all the work here, so I didn't show any false paths I might take. I didn't show any of the trial and error that takes to find the correct parameters, but be assured it takes trial and error to find correct parameters for anything, and there are false paths you might take down the road, but hopefully in the end you have everything running. So yes, experience helps, but there's a good load of just test and see what runs. So I don't want to extend anymore. I think it's already 9 o'clock here in Western Europe. So I'll be closing here. Thank you all for coming, and see you around on the conference chat and everything.